You know, we're surrounded by this massive industrial infrastructure, power plants, refineries, things we rely on every single day. But have you ever stopped to wonder how we know they're safe? Well, today, we're going to pull back the curtain on a hidden technology that works completely unseen to prevent disaster. Seriously, just think about this for a second. We're not talking about some big leak you can see with your eyes. We're talking about a tiny bit of corrosion, a little crack, a weak spot deep inside the metal wall of a pipe that could be miles long. How on earth do you find that before it's way too late? And get this, the scale of the problem is just immense. These aren't just any old pipes. They're ferromagnetic, which is really just a fancy way of saying they're made of steel or other magnetic stuff. They are literally the circulatory system of our industrial world. And having them fail? Yeah, that's just not an option.
So, how do we tackle this massive challenge? Well, the answer is a brilliantly clever piece of physics called remote field testing, or RFT for short. Now, the key phrase here, the really important one, is non-destructive. We don't have to cut anything open to look inside. Instead, RFT uses a low-frequency electromagnetic field, kind of like a searchlight, letting us see right through solid steel to spot flaws from the inside out. The way this works is actually pretty elegant. Think of it like a call and response. One part of the tool, the exciter coil, sends out a shout. But this shout, this magnetic field, doesn't just travel down the inside of the pipe. It travels through the metal wall, runs along the outside, and then pops back in further down. Then a second coil listens for that shout to return. If there's a flaw, like a thin spot from corrosion, it changes the sound of that returning shout. And that little change tells the inspector, hey, we've got a problem here. Okay, so this tech is amazing, right? But it's only as good as its setup. You can't just stick a probe in a pipe and hope for the best. Before you do any real inspection, you have to teach the instrument exactly what it's looking for. It's a lot like training a search dog, right? You have to give the dog a scent, an example of what it needs to find. In RFT, we do the exact same thing. We have to show the machine very, very precisely what a flaw looks like on its screen. And this is the tool for the job. This isn't just some random piece of pipe, you know? It's a reference standard, a practice tube with perfectly machined flaws of known depths, a spot that's 25% through the wall, one that's 50%, 75%, and a hole that goes 100% of the way through. This is the scent we give the machine. And here's what you get from that practice run. When the RFT probe passes that 100% through-wall hole, it creates this perfect, clean signal on the screen. This distinctive shape is the electronic fingerprint for a major flaw. The machine is now calibrated. It knows exactly what to hunt for. All right, so the instrument is calibrated, it's ready to go. Now for the real test, moving from the clean, predictable world of the lab into the messy reality of an active industrial plant. So the actual inspection, it involves pulling that probe through the entire length of a real-world tube. And the official procedure is super strict about this. It has to be done at a perfectly uniform speed. Any little variation could mess up the signals, so precision here is absolutely key to getting data you can trust. And this is where things get tricky. Here's the crucial difference. Real-world pipes aren't empty and isolated like our practice tube. They have support plates holding them in place, they have bends, all sorts of other features that create their own magnetic signals. All this noise can easily hide or distort the signal from a genuine flaw. And wow, this slide just lays it all out, doesn't it? On the left, you've got that perfect, clean flaw signal from our calibration. But on the right, that's the real world. The flaw is still in there, but its signal is all tangled up with that big, swooping signal from a tube support plate. This is where science really becomes an art. So how in the world do inspectors untangle that mess? Well, this quote from the official standard holds the key. The phase angle and amplitude are just technical terms for the shape and size of that signal on the screen. Highly trained analysts know how to look at that distorted shape, mentally subtract the noise from the support plate, and still accurately estimate how deep the real flaw is. It's a pretty remarkable feat of data interpretation, for sure. So, after all this, after sending fields, calibrating probes, and interpreting these crazy, distorted signals, what happens next? Well, this is where all that data gets turned into a critical safety decision.
And let me tell you, this whole process is incredibly rigorous. This is not guesswork. As you can see from this procedure, everything is controlled. If an inspector changes an essential variable, something critical like the test frequency, they can't just keep going. Nope. They have to requalify the entire procedure from scratch to prove it still works. This makes sure every single test is reliable and repeatable. All of that hard work, every setting, every little squiggle on the screen, it all comes down to one thing: the formal examination report. This document is the final product of the entire inspection. And believe me, this report is thorough. It documents absolutely everything: what pipe was tested, who tested it, what their qualifications are, the exact equipment settings they used, and maybe most importantly, a detailed map showing the location and the size of every single flaw they found. And that's the whole point, right? This report is the final, crucial link in the safety chain. It gives the plant engineers the hard data they need to make the call. Can we leave this in service? Do we need to schedule a repair? Or do we have to shut it down right now? The entire complex process comes down to making that one vital decision possible. You know, remote field testing is just one example of this incredible, unseen science that keeps our world bolted together and running safely. It makes you wonder, doesn't it? What other invisible tests are happening all around us every single day, quietly preventing disasters we'll never even know about?